Good morning, students. Today I'm going to teach Unit 4, so-called analytic functions. Okay. So in this chapter, before going to the problems and everything, the basic definitions we have in this unit. So I'll step by step, I'll define the definitions, try to learn, understand. Definition number 1, I'll start from the first definition, so-called, which is very basic for this unit, complex variable. First definition is complex variable. Yes, complex variable. The quantity z equal to x plus iy. The quantity z equal to x plus iy, where x and y are two independent real variables, is called a complex variable. The organ plane in which the values of z are represented is called z plane. Z plane. Okay. So in a simple way, I'll say usually we used to define real numbers and real axis. Real axis minus infinity, plus infinity, 0, minus 1, minus 2, etc. and 1, 2, 3, etc. So these are all real numbers. Actually speaking, x and y takes only the real numbers. So what do you mean by complex variable? As everyone knows, I'll draw the complex numbers like here minus 1, minus 2, etc. minus infinity, here plus 1, 2, 3, etc. plus infinity, it goes on. Okay. So actually we used to represent complex variable only in this plane. Very, very important plane. For everything we used to take this plane. So x and y. Say for example, I want to represent z is equal to 1 plus I. How to represent this 1 plus I? So actually, what is the value of x? 1. Y value is 1, like somewhere here. So I'm representing. Usually used to represent real numbers somewhere like here and here, right? In real numbers, real axis used to represent, no? Just like that, we used to represent the complex variable in complex axis like this. Say for example, z equal to 2 plus 3i, like 2 comma 3. So x value is 2 and y value is 3, something like so. As it is goes on. Okay. So whatever may be the definitions like continuous function, limit, what we deal in real numbers or real axis, same thing we are going to see in complex analysis also. So same thing we are going to see here. The function, whatever we represent in complex variable, we used to call that as analytic functions. Yes, step by step we'll go here. Yes, so this is the first definition, so-called complex variable. Actually, we are representing this in terms of Cartesian form because x and y, we can represent the same complex variable in polar form also, like which is equal to, or x plus I was, which is equal to x as r cos theta we are taking and y as r sin theta. So which is equal to r e power I theta. I can represent in polar form also r e power I theta, which is called modulus amplitude form of z. Modulo amplitude form of this z. Okay. So first definition is over. Next definition I'll say. So next definition is neighborhood. Second definition is neighborhood. Neighborhood. So how to represent? I'll teach neighborhood. So neighborhood. Yes. Neighborhood of Z0. Neighborhood of Z0 is the region of the Z plane consisting the set of points of Z for which modulus Z minus Z0 less than rho. So we used to call this as neighborhood of Z0. I'll teach here. As I said, whenever we enter into this complex variable, imagine the plane, then only the explanation will be more better for you. Like complex here. So I'll have drawn the complex variable here. So minus infinity, plus infinity, 0, 1, 2, 3, minus 1, etc. Similarly here minus 1, minus 2, etc. Here 1, 2, etc. The process goes on. Okay. So what do you mean by neighborhood? Say for example, I'll take this x0, z0 as x0 comma y0, which takes s, or we will take this as 0 comma 0. So z0 is x0 comma y0, which is nothing but 0 comma 0. Modulus z minus z0, which means, so this is nothing but 0 comma 0. Okay. Say for example, I'll take this row as 1. We used to call row as radius. Radius is 1. So I'll get a graph like this. So I think you can consider this graph of radius 1 I said, right? Yes, x naught, y naught, 0, comma 0 of radius 1 means the graph will be like this. Yeah, this is actual definition for the neighborhood of z naught. So this is z naught. So the points, set of all points in the neighborhood, that's all. So nearer to this z naught, what are all the points I can draw of radius 1? So somewhere point here, here I can represent one point here, one point here, one point here, one point. As a whole, we used to call this as neighborhood points of z naught. Actually, this is 1 z, this is z, this is z, this is z, this is z. That's why z minus z naught is less than 0. So we used to call this as neighborhood, which plays an important role in the further chapter so-called complex integration, particularly in Cauchy residue theorem. We'll apply this in Cauchy residue theorem. Okay, next definition is function of complex variable. So next definition is function of a complex variable. So function of a complex variable. Yes. So okay, we came to this we entered into this complex variable here. Then how to represent a function here? So whenever we say function, definitely it should be defined first. Whatever may be the functions we are taking here, it must be defined. Defined in the sense, what is the meaning for this defined? Which means exist. So defined means exist. So that's the actual definition, the meaning for this definition in math. So function of a complex variable I'll teach here. So z equal to x plus y. So I'll take two plane. I'll consider two plane here. Now I told what do you mean by complex plane. In order to define a function, we must take two complex plane. Like, shall I take this as z plane and this as w plane? Yes. So this is w plane and this is your z plane. Same represents the complex variable only. So here the variable whatever we have in z plane, which is nothing but x plus iy. I can represent x comma y like 1 comma 1, 2 comma 1, minus 1 comma 2 somewhere this plane here, this plane, any point I can represent. Similarly, w is nothing but u plus iv. So I can represent any point in terms of u and v. So this is the main thing. So now I'll teach what do you mean by complex variable. I mean function of a complex variable. Be two complex variables such that for every point z in a certain region R of the z plane, for every point over here, there corresponds one or more values of w. I mean in this w plane, there corresponds one or more values of w. Then w is called a function of z and is written as w is equal to f of z. I'll represent in one word c. So this is nothing but function f. So I can represent this w, w plane as f of z. So f is a function from this domain to this codomain. So this is your domain, this is your codomain. I can see the image of this object in the domain, in my codomain. Same concept here also, image, pre-image, I can find like f of z here. So actually what do you mean by function of a complex variable? I mean w equal to f of z, which means for each point z, say for example z1, z2 or z3. Z1 means somewhere in the first quadrant or second quadrant, third quadrant, can be any point. I'll get the corresponding point in w plane. If I give one example like this, I think you can understand in a easy way. See, w is equal to z square I'm getting. Okay. So z, for z equal to say for example z1 means 1 comma 1 shall we take? Yes, z1 is equal to 1 comma 1 means what I'll get? Z1 1 comma 1 means w will be 1 plus I. 1 comma 1 means I have to multiply my imaginary part along with my y value, no? So 1 plus I the whole square. So I'll get similarly the one more point, some point like in terms of real and complex variable. Okay, if you expand this 1 square plus 2i plus I square, so something like 0 comma 1 or 0 comma 2 some point I'll get 0 comma 2i like that. The same point exists in this w plane. This is the actual meaning for the function of a complex variable. Next, so this example you can take w equal to z square For each point in the Z plane, I'll get the corresponding point in the W plane using this function. Okay, so this is definitely one more definition. One more thing I want to add, whenever we come to this function or for complex variable, we must know what is the meaning for single valued function of Z. Okay, what do you mean by single valued function? So actually W equal to Z square is a single valued function, of course. So single valued function. Single valued function means for all values of Z, if you substitute for all value of Z in the sense 1 comma 1 minus 1 comma 1 or 2 comma 2, whatever may be the points you substitute, I'll get only one value somewhere here. Corresponding point, I'll get only one value here in my W plane. So we used to call this a single valued function. Then what comes the other thing like multi-valued function? Multi-valued function means one or more points I'll exist. Suppose, say for example, 1 comma 1 you're substituting in Z, but the value how I'm getting, like plus or minus 2 or more values I'll get in this W plane. So we used to call that as multi-valued function. Whenever I get only one value, single value means I used to call this a single valued function. Okay. Next definition is limit. Next definition is limit of a function. What do you mean by limit? So limit of a function, that is clear in this definitions, and then I'll go for the problems as usual in a quick manner. Before that, we must learn certain definitions in analytic function, which is very useful for the last chapter 2. So the basic definition what I'm teaching here, it's very, very important for your next chapter also. I mean the 5th chapter, so-called complex integration. Yes. So next definition is limit of a function. So let f of z be a function. Let f of z be a function in a domain D. Let f of z be a function, which means as it is function f from z plane to w plane, and then w is equal to f of z, I can represent w as f of z, the same concept here. Then what do you mean by limit of this function? Okay, I'll teach limit of a function. F of z be a function defined in a set D, and z not be a limit point of D. Then A is said to be a limit of f of z at z naught if for every epsilon greater than 0, there exists a del greater than 0, such that modulus f of z minus a less than epsilon. Modulus f of z minus a less than epsilon. So this is the definition in math we used to define for all z and d. For all z in domain D, it should satisfy this condition. Then we used to call this as limit of a function. Okay, in cut short or clear, I'll teach the another definition of this limit, like limit z tends to z naught f of z equal to a whenever modulus z minus z naught less than 10. I'll say actually del is a very, very smaller number, which means as z tends to z naught, as z tends to z naught, as I said, x naught, y naught. So z is nothing but all values of z, like 1 comma 1, 2 comma 2, 3 comma 2. As all the values of z, whenever it nearer to this 0 comma 0, I mean the origin, we can take, suppose origin also can take 0 comma 0, the corresponding f of z, it will tend to some value a or limit, some limit. We used to call this as a limit of a function. Okay, so this is z naught, as z is nothing but all, so imagine whenever I draw domain, this is nothing but complex plane z naught, so 0 comma 0. As z tends to z naught, so all values of z, so here one z I can define, here also I can define one z, z1, z2, here I can define z3, here I can define z4. So it is true for all the values of z. So as z tends to z naught, or z1, z2, z tends to z naught, the corresponding f of z, in codomain we used to define this f of z, that tends to a. So this is the definition. Whatever may be the point you are defining. Say for example, I need z1. I am defining z1 in this domain. What will be my f of z? I mean, what will be my function in a w plane? Corresponding function f of z1. As I said, for each point z, single valued function exists. Therefore, z1 exists. As z tends to z0, the corresponding function f of z1 tends to certain value. This value a, used to call this as limit of the function what you define here. Okay. So this is limit of a function. Next. So next definition I'll go for continuity of a function. I think students you're all clear in this limit of a function. Shall I explain it again? See here. Limit of a function. So this is your W plane. This is your W plane. This is your Z plane. Okay. So I'm defining actual definition is this as limit Z tends to Z naught. F of Z tends to A. When it tends to A, whenever modulus of Z minus Z naught less than del, which means as Z tends to Z naught. This is the actual meaning. Because less than del means del is very very nearer value, very very smaller value. When a very very small means obviously z tends to z naught. Only for that we are defining this del over here. So whenever z tends to z naught means this in the through the graph you can see here like z tends to z naught in the z plane. Corresponding f of z, for each z corresponding f of z exists. Yes. Corresponding f of z tends to a. So this is the definition of limit of a function. Okay. So imagine this function can be like z square, z cube, or what 2 times of z, 4 times of z, whatever may be the function you are giving. That must be defined actually. So whatever may be the function you are defining here, it should satisfy this condition. So definitely for z square, you will have certain limit like e, just like e, this function may have, this z cube may have, this 4z may have. Okay. Okay, I think this definition is enough now. I'll go for the next definition, so-called continuity of a function. Next definition is continuity. So next definition is continuity of a function. Continuity. Students, have you heard about continuous of a function? Same concept here also. Already I taught you this continuous function in the class. Same thing. So same thing existing in this complex variable, complex plane also. The z plane, continuity function also exists. Like as per the definition I'll go. A function f of z is said to be continuous at z equal to z naught if f of z naught is defined. If f of z naught is defined, underline the word defined. Defined means, as I already told you, exist. It should exist. Then only I can find the continuity of this function. Otherwise, I couldn't. So exist if f of z naught is defined and limit z tends to z naught, f of z equal to f of z naught. Yes. So this is nothing but continuity of a function. Yes, limit z tends to z naught, f of z as limit tends to z naught, f of z tends to f of z naught. If this equation, if it is true, means used to call this function, f of z as a continuity of a function or continuous function. Both represent same only according to my view here. So actually, can I represent this in terms of 2D so that everyone can understand in an easy way? See here, look into it. Say for example, I'm representing in 2D. Say for example, here Z lies. Z in the sense, imagine your complex, complex plane, all the values of Z. Okay. Okay, here Z naught. Z naught means somewhere origin or some other point, 1, 1 or 2, 1, some other point somewhere here. Okay. So as z tends to z naught. So as I said, for each value of z, definitely you will have f of z. Yes or no? So for each value of z over here, this is your z plane. As I said, this is your w plane. For each value of z here in the z plane, definitely you will have corresponding f of z in W plane. You agree? Yes. For each point z, you will have corresponding point. I mean, f of z in W plane. Say for example, similarly, z naught if you have, definitely f of z naught you will have somewhere here. Okay or not? F of z naught exists depending upon the function what you have defined. As I said, f of z naught should be defined in the sense like z square or z cube. It should be defined like this, z square, z cube. Whenever you define like this, corresponding f of z exists over here? Yes, definitely it will exist. Yes. Actual definition of continuity function is this. Corresponding f of z tends to f of z naught. This is the definition of the continuity of the function. As z tends to z naught in the W plane, z plane, corresponding f of z tends to f of z naught in W plane. So this is true for all value of z, whatever you define here. It must be true for all value of z. Whenever it is true, you used to call this function f of z is continuous function. Can I represent in terms of graph like this function is continuous? As it is, however we are defining in real numbers or real axis, we used to define no same concept over here. Here also we used to call this as same thing only. Suppose this curve is discontinuous and this curve is continuous. Continuous in the sense each point of z we are defining here. Okay or not? So for each point of z tends to z naught or for all values of z, so corresponding f of z we are defining. Substitute 1 comma 1 or 2 comma 2 minus 1 comma 1, all values substitute, will get the graph like this. In terms of continuous curve, that too. It is not discontinuous. In terms of continuous curve, I'll get. Okay. So this is nothing but continuity of a function. In one word, I'll say as z tends to z naught, f of z tends to f of z naught. So this is domain. And this one is codomain. I mean, this is domain. And this one is codomain. Okay, I think I'll go for the other definition, continuity of a function I said. So next one example I'll give. Whether the function is continuous or not, I'll give an example. And then I'll go for the other 2 to 3 definitions I have. That's all. I'll go for the problems after that. Example. I'll consider this example. F of z. They themselves have given in terms of question itself. If f of z is equal to 3x square plus y square by x plus y the whole square, show that limit z tends to 0, f of z does not exist. Yes, limit z tends to 0, f of z does not exist. What they try to say here, the function f of z does not exist, they say. For what type of function? What they have defined here. As I say, the definition what we have defined should be clear, whether the only based on that only we can say the function is continuous or discontinuous or anything, whatever we want. So here they said in the question itself, the function f of z does not exist. So we have to give a proof for this. We'll give proof. Before that, try to understand the function f of z does not exist, they are saying here. Does not exist in the sense it is discontinuous. Okay, so does not continuous means, does not exist means the function f of z is discontinuous. I'll prove why I say this function f of z is discontinuous. Just wait and watch. Okay, they have defined the function as 3x square plus y square plus x plus y the whole square. I think this is arbitrary, like x comma y for all values of x and y, I'll get different thing. But I don't have definite path for this function, isn't it? I don't have a definite path. So path in the sense I need certain thing for defining or for whether the function exists or not, I need a path. Because it by seeing this function, it is very difficult to find. Okay. So I'll consider solution or proof you can take. I'll consider y equal to mx here. This is nothing but a path. As everyone knows, y equal to mx. It's a path. Through this path, I'll check whether the function f of z is exist or not. Yes. Let us define. According to the definition of the continuity, I'll take limit z naught tends to 0. What do you mean by z naught over here? Z naught tends to 0 means what? X naught, Y naught tends to 0, which means I'm defining the point 0 as 0 in terms of origin, like x0, y0. That's the meaning, right? X naught means what? X naught comma Z naught means what? X naught, Y naught. X naught, Y naught is nothing but x0, y0. Okay, I'm defining in such a way. So x tends to 0, y tends to 0. Okay, in domain. I mean in domain. Yes. Coming to the function here, I have to take y as mx, isn't it? So 3x square plus m square x square divided by x plus mx the whole square. And then as usual I have to substitute x0, y0 it seems, no? Yes, x0, y0 I have to substitute. Here I think I converted everything in terms of x. So I'll take the limit as x tends to 0. And then I'll check what I'm getting here. Just wait and watch. So here I think I can cancel this x square, isn't it? If I take x square, see here, if I take x square, 3 plus m square. The denominator, if I take x square, 1 plus m the whole square. So x square get cancelled, and then as it is, I have to apply limit x as x tends to 0. But I couldn't find any x over here. If I, after cancelling, I couldn't find any x over here. Okay. Yes, I couldn't find anything like that. Now, just wait and watch what value we are getting here. So it means for different values of m, I'll get different values of this f of z, isn't it? Yes. Different values of m, I'll get different values of f of z. As I said, you all remember, for each value of z in domain, I'll get the corresponding value in codomain. So in my codomain, what value I'm getting here? See. So for m equal to 1, 2, 3, if you substitute, for arbitrary, if you substitute, I'll get different values of f of z. Is it possible? Definitely, it is not a single valued function, I agree. But apart from that, whether for any function it may exist like that? No. So which means that the function f of z does not exist. What to define here? Not for all the function. The function what they have given you or what they have defined. For this function only I am talking. So the function f of z does not exist. Okay. Okay, here I have one question. If the function does not exist, what about continuity of the function, exist or not? Or otherwise, the limit exists or not for this? Definitely not. Limit does not exist. Different values if you get, whether the limit exists, for different values of m, I'll get different values. Whether the limit exists here. So please be careful in this thing. It's very, very important. You just understand the idea, that's enough here. See here, once again I'm repeating, y equal to mx I'm taking as a path for this function. They have defined the function like this, and they said that a function f of z does not exist. So how to know whether it exists or not? For that I have to give the proof. Yes, what I have taken here, y equal to mx I have taken. I need certain path for this function in order to represent whether the function exists or not exists. I need a path. So I have taken y equal to mx. And then limit, as I said, limit I have taken z not tends to 0. So generally I can, so you may have, I mean, question in your mind, or you can ask this question, why we are taking 0? Like as usual. So if they don't give the limit, they didn't specifically, they didn't give the limit over here. So I can take that x and y as 0. Okay, I can take the point z tends to 0 comma 0. Yes or no? So z tends to 0 comma 0 means, as I said, all the values of z. So here comes 0 comma 0. So this is nothing but 0 comma 0. As z tends to 0, all values of z tends to 0, what happens? Let us find the corresponding f of z. So for that only I said I have taken a path as y equal to mx. So I have taken a path something like this. So y equal to mx m square x square. After cancelling, this is a simple process only. After cancelling x square goes, and then I have to take x tends to 0 because I don't have y here because I converted. So only x remains. So as x tends to 0, I'm getting this equation. Which means m is nothing but what? For m takes all the arbitrary values like 1, 2, 3, 4, etc. So how does that possible? So for f of z, I'm getting different values of m, isn't it? So definitely, if we get like this, the function f of z does not exist. Okay, clear in this? Yes, one more example I'll give and then I'll go for the other definition so that you will be very clear in this. 1 minute. I'll give one more example. The second example is this. Show that the function f of z defined by, show that the function f of z defined by 3x square plus y square divided by x plus y the whole square. Yes. Comma, is that not equal to 0? And then the function, how they defined, I'll write. So here 0 it seems whenever z equal to 0. Which means what z equal to 0 means? F of z 0. Is it not equal to 0 means the function exists like this. Yes. They say it's not continuous at the origin. So they say it's not continuous. It's not continuous at the origin because I'm getting 0. How does it continuous? So it is not continuous at the origin. Okay. So this is one more example. Since the limit does not exist, the function is not continuous at the origin. Yes. So one more word I have to add here. Whenever limit does not exist, the function is not continuous. Yes, of course, I have to tell in this example, I have to say whenever limit does not exist. I told you how to find the limit, everything I told in the previous definition. But for this function, if limit does not exist means, obviously, the function is not continuous. Whenever the function is not continuous, it may not exist also. Then how if it is not continuous means, how does the function exist then? The curve goes like this. Disconnectivity happens here. Then how does the function exist? We can't find the limit or convergence of this convergent series of this function or something like that. I can't find anything whenever it is discontinuous. Okay, we should be very clear in this continuity of a function. Okay, next definition is derivative of a complex function. I think we're all clear in this. Next definition is, so next definition is derivative of a complex function. So what do you mean by derivative of a complex, derivative of a complex function? In one word I'll say, in terms of equation I'll give you and then I'll explain. That will be easy to understand. Like f dash of z naught will be equal to limit del z tends to 0 f of z naught plus del z minus f of z naught divided by del z. Already you might have studied in your real analysis itself. Real numbers. Using real numbers, we might have studied. Like, see here, f of x plus del x minus f of x by del x. You might have studied this. As I said, always same concept in complex plane. That's all. That is the main difference between that and this. We are defining this function in complex plane. That's all. Okay. As it is, as I said, z naught means what? Always, whenever you write z naught, imagine x naught, y naught. Okay. So x naught, y naught, like any point in the z plane, f dash of z naught. So f dash of z naught means derivative of f of z. When does derivative exist? When does derivative exist? Usually you just imagine your real numbers. How we'll define f dash of x means what? So a point which moves from in one dimension, I think in one dimension I'll teach here. Whenever a point in the axis I'll teach, whenever a point moves from one point to other point, differentiation occurs. Like this is x, isn't it? This is del x. Okay. The difference between this is nothing but del z. Okay, in terms of complex variable itself, I'll explain. See here, this is your z naught and this is your z naught plus del z. In how comes the derivative? Only in this way it comes the derivative, like z naught. This point is nothing but whenever the point moves from here to here, z naught plus del z. The difference of the distance, the difference of this both the points is nothing but del z. Yeah. So f of z naught plus del z, the function f of z naught plus del z. This is nothing but z naught plus del z in the always remember z naught plus del z in the z plane. F of z naught plus del z will always be in the w plane, the other plane. Okay, whenever you write, imagine, then only it will be interesting. So as I said, f of z naught plus del z minus f of z naught. Okay, yes. So divided by the difference between the two ends is del z, where the limit del z tends to 0, I'll get the derivative f dash of z naught. Derivative of a complex function. So this is nothing but derivative of a complex function. Isn't it? Yes. Next, now only I'm entering into the concept of your analytic function. It will be easy if I teach what do you mean by analytic. If you know the basic concepts, everyone can understand the analytic function in an easy way. Analytic function. What do you mean by analytic function? So before going to the definition, I'll tell you the other name of analytic function is regular function, holomorphic function. Now I'll tell what I mean by analytic function and then I'll explain. Let me see. A single valued function f of z. A single valued function f of z is said to be analytic at a point z naught. You know, whenever I define a point, imagine the point z naught is in which plane? Always remember. So z naught means what? In z plane. Okay. F of z means what? F of z always will be in w plane. Yes. Now I'll teach. A single valid function f of z is said to be analytic at a point z naught if it has a derivative at z naught and at every point in some neighborhood of z naught. Okay. Say for example, the point z naught is in the origin. I'll take like that so that everyone can understand in an easy way. I'll take this z naught as 0, 0. And then what is neighborhood of z naught? Yes, already I defined the previous definitions. So neighborhood of z naught means what? So all the points like here, 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 here. Okay. Inside the circle but not on the circle. Yes, because less than rho only, no, according to the definition. It doesn't include the radius. So all the points inside the circle. Okay, it's fine. It's like this. Now what do you mean by analytic? A single valued function. Analytic means a function f of z should be, point number 1, should be single valued. I told you the meaning for single valued function in the beginning itself. Said to be analytic at a point z naught. Which point we are defining here? At a point z naught. If it has a derivative at z naught, which means z naught means 0, 0, I'll take. So it should have derivative means, say for example, I'll take f of z as z square. The function what I'm defining, the graph will be like this. Z square I'm taking. Whether the function f of z has derivative, yes, of course, I can differentiate this derivative only. Just now I explained the previous definition. What do you mean by derivative? Differentiation only derivative. I told you how we are getting the derivative. Definition I told you, but what do you mean by derivative? Actually differentiation only. See here. So can I differentiate this? Yeah, 2 times of z? Yes. So all satisfies here. So what do you mean by analytic function? Single valid function. And then it should have a derivative. If it has a derivative, at what point we are defining z naught? Okay. So at z naught, it should have a derivative. Not only at z naught, at every neighborhood point of z naught, it should have a derivative. Say for example, here is z naught. Say for example, here can I represent this point as z1? As minus 1, 2 or minus 1, 3, something like that I can represent. Yes. At this z1 also, this f of z should have a derivative. At z2 also, it should have a derivative. At z3, which is inside the circle only. So this is the actual definition of analytic function. Okay. Yes. Next. Okay, analytic function I have defined for you. So we have certain thing like necessary condition for the function f of z to be analytic. And sufficient condition also we have for f of z to be analytic. So you need not worry for these things. Just the necessary condition for the function f of z to be analytic. For that, it should satisfy Cauchy-Riemann equation. What equation it should satisfy? Cauchy-Riemann equation. So very, very simple. I'll write the necessary condition here. So necessary condition for the function f of z should be analytic. What is the necessary condition for the function f of z to be analytic? It should satisfy Cauchy-Riemann equation. Cauchy-Riemann equation. The other name I'll give for this, we used to call this a CR equation. So we used to call this as what? CR equation. So they have been defined. So you need not very see the thing. See here, I'll write the definition. I mean the condition for this CR equation. For the CR equation, the condition is this: Ux equal to Vy and Uy is equal to minus Vx. So hereafter, what we are going to study, what we are going to deal, whether the function what you are having, what you are taking in your hand, like z square, z cube, z plus z cube plus z square, it may be anything, any polynomial of higher polynomial. The thing is this, hereafter you are going to identify whether the function f of z is analytic or not. Hereafter we are going to deal these things, whether the function is analytic or not. So for that we must understand the Cauchy-Riemann equation. I mean the Cauchy-Riemann equation, like Ux equal to Vy, Uy equal to Vx. By seeing Ux, I think we all remember what do you mean by this actually? Partial differentiation of U with respect to X. Partial differentiation of V with respect to Y. Similarly here, Uy, this is minus Vx. Why Uv? In here function f of z we are representing. Where will define this function f of z? In z plane or w plane? U comma v means in w plane, x comma y means in z plane. So obviously I said function f of z only we are dealing now. So I mean the function f of z, whether it is analytic or not, only we are dealing. So it should satisfy this condition: ux equal to vy and uy equal to minus bx. I'll give you an example. So before going to that example, I'll tell you what is sufficient condition. So just both condition are very, very important. So sufficient condition, I'll tell what do you mean by sufficient condition. For f of z to be analytic, the function what you take in your hand should be analytic. What is the sufficient condition? Point number 1. U and v are differentiable in the domain. Okay, so u and v means what? As I said, uv, corresponding uv will get, right? Suppose f of z is nothing but what? W is equal to, z is nothing but what? X plus I by the whole square. So once again, w is nothing but what? U plus iv. So I think we will expand and do whatever you want. Definitely will get real and imaginary part, isn't it? Yes. So I'll have u in terms of something like xy or real part, I'll get it. Similarly, v I'll get in terms of imaginary part like xy or x square or something, I'll get it. Okay. I'll get u and v separately, isn't it? Yeah. Here comes the thing. So u and v have to, what they say, u and v are differentiable. I have to check whether u and v are differentiable or not. Okay. And one more condition is here, like ux equal to vy and uy is equal to minus vx. Same condition. I mean, necessary condition, you know. Same thing, sufficient condition also should satisfy. Here also it's same thing exists here. Provided u and v are differentiable and it should satisfy this condition. This is point number 1 for sufficient. Point number 2, you know, what is it, you know? Point number 2, the partial derivatives. What are all the partial derivatives of ux, uy, bx and vy? Okay, are all continuous. Are all what? Continuous. This is the second most sufficient condition. What is it? Ux, uy, bx, vy are all continuous. I told the meaning for continuous already. Continuous means, I think you know. So the graph should be continuous. It won't discontinuity. It does not have discontinuity at any point. So ux, uy, bx, y are all what? Continuous. Okay. So this is very, very important concept of this analytic function. So what do you mean by necessary condition? What do you mean by sufficient condition? Everyone must know these things. Then only we can enter into the problems. The basic what I taught in this session, everyone must know. Just recall the things. Then only we can go for the problems in a easy way. So once again, I'm repeating analytic function. So necessary condition. So necessary condition means what? So this is Cauchy-Riemann equation. It should satisfy. That is going to be our necessary condition. Like ux equal to vy and uy equal to minus of vx. It should satisfy this condition. What do you mean by sufficient condition? U and v should be differentiable. Ux equal, and it should satisfy the CR equations also for sufficient condition. One more condition for sufficient condition. What is that? Ux, Uy, Vx, Vy are all continuous. Okay. One example I'll give for this analyticity. One example I'll give. One example. What example is that? Examine the analyticity of the function. So same function only they are also introducing here. Analyticity of f of z equal to what? Z square. Examine the, I'll repeat the question. Examine the analyticity of the function f of z equal to, what is that? Z square. Okay, fine. Okay, let us wait and watch. So what do you mean by f of z here? W. What is z? Z is nothing but x plus iy. So z square means x plus iy the whole square. Okay. So imagine f of z is in w plane. That's why, I mean, as everyone knows, w. But what do you mean by w here in terms of uv? All the variables in w plane we are represented in terms of u and v. Yes. Can I write like this? U plus iv? Yes. Coming to RHS, expand, that's all. X square plus a square plus b square, okay, minus y square plus 2 into ab, 2i xy, isn't it? Now, can you tell me what is u here? X square minus y square. What do you mean by b here? b here, 2 into x into y, isn't it? Yes, x square minus y square here. What is the value of b here? 2 into xy. Yes. They ask whether the function f of z is analytic or not. What do you mean by analytic? It should be differentiable. Recall now. What do you mean by what is the definition of analyticity? Recall yourself. Analytic means it should be a single valued function, and then it has a derivative at z naught, and at every point in some neighborhood of z naught, which means you just imagine that neighborhood naught everyone knows, I think. So the function should be single variable. I mean, single valued function should be single valued function and should be differentiable. Okay, I think by seeing itself, it's clear that it is differentiable. Okay, so so that I can proceed now, only for that I checked this. Okay, I have to say whether it is analytic or not. Analytic means if it satisfies our CR equation, I can say analytic. The function is analytic. Okay, if it doesn't satisfy CR equation means it is not analytic. Okay or not? As I said, for certain function, I can find the derivative for this. For certain functions we have, which is very difficult to see. By seeing, we can't say whether it is differentiable or not. For certain cases we have. Only for that purpose, they have introduced a CR equation like ux should be vy. What is the other condition? Uy equal to minus vx. Okay. Only for that purpose, they have been introduced a CR equation. So it is easy for us to verify whether it is the function f of z is analytic or not. Let us wait and watch. For this, what is ux? Ux means, as I said, it's partial. Be careful. X means y constant. Y means x constant. So 2x. What is uy? Minus 2y. What is vx here? Vx is 2y. What is vy here? Vy is 2x. Let us wait and watch. What is ux here? 2x. So I'll verify the first condition. So ux equal to 2x. What is vy? Vy equal to 2x. Satisfied? Put a tick. Next, what is uy here? Minus 2y. What is minus of vx here? I'll write minus over here. Yes. What is vx for us? What is vx here? I can find here 2y. So minus 2y. So both condition satisfied. So CR equation satisfied, verified. So if CR equation satisfied, then obviously I can say f of z is analytic, is